Hi, thanks for tuning in to your chemistry video today. Let's go ahead and get started with our learning targets for the unit under pressure. The first learning target is I can list the 4 variables that affect pressure of a gas. The second learning target is I can summarize each gas law and identify the graph that represents each law. And then the third learning target here says I can summarize the kinetic molecular theory. That's K-I-N-E-T-I-C. It's kind of rubbed off there a little bit. Okay, so make sure you get those learning targets down so you know what you'll be learning. Okay, so like I said, there are 4 variables that affect the pressure of a gas, and they are listed here for you. Volume is one, and we always represent volume with a V. And of course, you probably remember that we measure volume in liters or milliliters. Temperature is always expressed with a T, and we measure temperature when we're doing work with pressure in a new measurement unit called Kelvin. And we'll work on those temperature conversions in class before we have to do any sort of pressure problems. But just so you can get this written down, in order to convert from degrees Celsius to Kelvin, you just simply add 273 to your Celsius temperature. I'll explain more about what that actually means when we get to class on Thursday. All right, and then C is pressure. So the third variable is pressure, and we represent that with a P. And we went over all of the units that we used to talk about pressure. We talked about the millimeters of mercury, atmospheres, and kilopascals, and also PSI, the pounds per square inch. However, we won't use pounds per square inch in chemistry. All right, and then the last variable that affects pressure is the amount of gas. And we represent the amount of gas with a lowercase n. And we always measure amounts of gas in moles of particles. Okay, because remember that gases are made up of particles. And because we're talking about many, many, many particles, we're definitely going to use the mole as the unit. Okay, so let's look at the first law regarding gases. Now, one thing I want you to understand about a scientific law is that it is a law because we see the relationship between the 2 variables involved in the law over and over and over again. And so a law is all about just describing phenomenons in the universe. And so Boyle's law is an example of that. And so I want you to write down that Boyle's law was written in 1662. So that's a very long time ago, and it still stands today. So we are very certain that Boyle's law describes a fundamental action that occurs between pressure and volume all the time, no matter where you are on the planet. Okay? So first of all, you can write down, well, what does Boyle's law tell us? And Boyle's law tells us, or gives us, the relationship between pressure and volume. So Boyle's law gives us the relationship between pressure and volume if the amount and temperature are held constant. So think about that for a second. We're trying to find the relationship between volume and pressure as long as the amount of gas in a container and the temperature are held constant. And what we know, based on the experiments that have been done on Boyle's law, is that if volume increases, so notice that I'm using V to represent volume. If volume increases, as I'm denoting with an arrow pointing up, if volume increases, the pressure decreases. If the volume decreases, the pressure increases. Okay, so think about that for a second and see if you can think of any examples of where when you have the volume expand, the molecules have more room to move around, so the pressure decreases. But if you make the volume really small, the molecules can't move around very much anymore, and so since the temperature is the same and the number of particles is the same, If you reduce the amount of space that things can move around in, then the pressure is going to go up. All right? This type of relationship where one variable goes up and the other variable goes down is called an inverse relationship. And we can show that on a graph. And this graph shows us, with volume on the x-axis and pressure on the y-axis, that as your volume increases, the pressure decreases. So we could even get more specific here and see that if the volume is doubled, the pressure is halved. And so they actually, the amount that the volume goes up is equivalent to the value of what the volume goes down. So what I just said is, if the volume is doubled, the pressure is halved. So if you increase the volume by 2, you're going to halve the pressure. If we said that we're going to increase the volume by 3 times bigger, then our pressure is going to go down by 1/3. Okay? So that's what we mean by an inverse relationship. All right. The next law deals with 2 other variables that affect gases. Charles's law was written in 1787. So once again, we're talking about science that was done many, many, many years ago, and we still see that it occurs according to these laws every day, all day. Okay? So Charles's law, written in 1787, gives us the relationship between volume and temperature, as long as pressure and amount are held constant. So once again, think about that. This is the relationship between volume and temperature as long as the pressure and the amount of gas molecules is held constant. So what we see regarding this law is that if your volume increases, the temperature increases. If your volume decreases, your temperature decreases. So when you have one variable that goes up and then the other variable goes up because of that, we call this a direct relationship. And we can see that on a graph here, where you see that as the volume goes up, the temperature goes up, and you get a diagonal line straight from 0, which is called a linear relationship, and a direct relationship. One thing I want to point out here is that there have been lots of scientists that have worked with this law, and there was another scientist by the name of Lord Kelvin, and he discovered, or he hypothesized, that if this is true, then if you got all the way to 0 volume, meaning no space, then you'd also have to get to the absolute lowest temperature. And he calculated that to be negative 273 degrees Celsius. However, using negative 273 in calculations is a little bit difficult. So he created a new temperature scale specifically to use with pressures that converts the Celsius temperatures into Kelvin. And so negative 273 degrees Celsius, which is potentially where all atomic motion would stop, is 0 degrees Kelvin. And that's referred to as absolute 0. So if the volume goes to 0 milliliters, then the temperature must be at absolute 0. All right, so make sure you write that down. Absolute 0 is 0 Kelvin. We don't use the degree symbol with Kelvin. All right, moving on. All right, the next law is called Gay-Lussac's law. This law was a little bit later. It was written around the 1800s. I don't have a specific date, but it was definitely later. And Gay-Lussac gave us the relationship between pressure and temperature when volume and amount are held constant. Okay, so once again, think about that. You're holding the volume the same size, and the temperature is the same. So the only thing that's changing, it's when the volume and the amount. So your volume is the same, and the amount of molecules are the same in there. So what's going to happen to the pressure when the temperature goes up or down? And this one is probably one that makes more sense to you because you already know what happens to molecule and particle motion when you add heat. It speeds up, right? So then you're having more collisions against the sides of the container and against all the other molecules. And so we can predict here that if the temperature goes up, the pressure is going to go up. If the temperature goes down, the pressure is going to go down. So think about that. What type of relationship is that? Both variables are doing the same thing. So that is also a direct relationship. And so you can see once again that shows us that we have a linear relationship between the temperature and the pressure. All right, and then the last law is called Avogadro's law. You've probably heard of that guy before, right? Avogadro's number is 6.02 times 10 to the 23rd. Well, Avogadro also did experiments with pressure, and his law gives us the relationship between volume and the amount of gas when pressure and temperature are constant. So it shouldn't surprise you that Avogadro's law deals with the amount of gas, which we measure in moles, remember? Okay, in this case, we found that if the number of moles of gas, so the amount, which we represent with the lowercase n, if this goes up, then the volume goes up, right? So this is, think about like blowing up a balloon, because if you put more air into the balloon, the volume of the balloon, the size of the balloon increases. If you let some amount of air out, then your volume is going to go down. Okay, so this one is kind of common sense. But you can also look at a graph of Avogadro's law that shows the same direct relationship. Okay, so remember that the learning target about the gas laws is that you can summarize the laws, and that takes a little bit of work. That's going to take a little bit of study that you can remember the Boyle's law, Charles's law, the Gay-Lussac's law, and Avogadro's law. Those are 4 laws that you need to know which is which. And you also need to be able to pick out the graph that goes with each one. So that's probably going to take a little bit of study on your part to make sure that you keep those straight. All right, so in science, when we make observations about things that happen, and all of the laws that were developed because of the work of those scientists were based on their observations and based on what they actually saw happening. But they didn't really understand why it was happening. And so many other scientists went to work trying to figure out why that is. And those scientists came up with what we now call the kinetic molecular theory. And as you can see, the kinetic molecular theory was developed, and it's still being developed. We always are looking for more explanations. In 1857. So this theory was developed well after the laws that were written down were developed. But the kinetic molecular theory explains, it doesn't describe what we're seeing, it explains what we're seeing. It explains the observed thermal and physical properties of matter. So let me talk about that just a little bit. What is a thermal property? Well, that would just mean what does the matter do when you add heat or take heat away. So it all depends on the energy that's associated with the matter. And then physical properties are the physical properties. What does it do? What does it look like? Okay? So there's 3 basic things that I want you to understand and remember about the kinetic molecular theory, which is sometimes abbreviated KMT. First of all, matter consists of tiny particles in constant motion, but you already knew that. B, the speed of those particles is proportional to the temperature. So what that means is as you increase heat, the temperature is going to go up, and that's going to cause your particles in the gas to move around a lot more, colliding with each other, colliding with the sides of the container. And then the third thing is that the impact of these particles on surfaces is what causes the pressure. So like we've already talked about with air pressure, anytime particles are pushing up against the sides of the container, then there's going to be pressure. So that's it for now. I look forward to seeing you on Thursday. Thanks. Bye-bye.